I just wanted to welcome Deb and welcome everyone to our third talk now in this Tertiary in Montana series that we sort of started just to get the conversation going about the tertiary, thinking about our upcoming TRGS that's going to be in Bannock this year and have lots of things going on there. But one of the things that we'll be doing is showcasing some of the bureaus work in the tertiary. So that was kind of the seed for this. And we've heard from two people so far, Bob Schwartz, who talked to us about the Renova, who talked about some decreasing ages as you go up section, and he related that to some unroofing event. And then Rob Thomas came to talk to us about the 6 Mile Creek with this impassioned argument that we should be mapping with lithostratigraphy for that. And that we have drainages that are really young. So we're super happy to hear from Deb about her work. She has been working in Montana and explaining the tertiary to us for a few decades. I have used her work for my work, and I know that several people in here have done the same. I don't know if she really needs much of an introduction, but she hails from Whitehall, right over the hill, which is nice for us. We're really thankful to have you here. And we look forward to hearing about everything you have to say. So welcome.
Oh, thanks. Well, thanks everyone. And I'll say another welcome to you all and also everybody in Zoom land. Just want to say, yeah, this is a great idea to have a forum on tertiary. Lots of different views. You know, we kind of coincide on similar data sets, but interpretations may vary. And that's always good because that sparks a good conversation. So what I'm going to do today is talk on Southwest Montana Cenozoic sequences, Paleosols a bit, and also trace fossils. To do that, what I'll do is I'll basically walk you through my progression to the use of sequence stratigraphy rather than lithostratigraphy. I'm going to talk a bit on, not only how I got there, but the stack up of sequences as we've defined them, talk a little bit about ongoing work that we're doing in terms of refining the ages of the sequence boundaries. And then I'm going to talk about regional extent of the major unconformities and what we may be able to draw out of that when we look from the Great Plains to Pacific Northwest, basically. Also, we'll take a break and we'll switch gears scale-wise and come back and talk about two Eocene sections, and their contained paleosols and trace fossils. And to do that, you've already heard Steve Hasiotis chiming in, but Steve is the trace fossil person that we've been working with. And so he'll pretty much take over at that point. We might tag team a little bit, but and then we'll just hope my voice holds out coming off of a cold. And looking at the cover slide, the other thing I want to say, it isn't just my work. It's people that I've worked with that we've been able to unravel some of Cenozoic history, because people that I've worked with really have different areas of expertise. And those areas of expertise really play into bringing out a complete picture of tertiary Cenozoic history. And I'll just kind of cite everyone. You can see him on the screen, but Chuck Wideman, emeritus from Montana Tech, geophysics, full disclosure, that's my husband, Don Lofgren. He's the vertebrate paleontologist, Alf Museum, and oh man, have I ever learned a lot from Don in terms of vertebrates. Steve Hasiotis, as I said before, trace fossils. I sent Steve some trace fossils and yeah, got him interested in coming out. And once again, I have to say, I really learned a lot and am still learning. And then, of course, Jim Halverson, the retired director of the Montana Board of Oil and Gas. And yeah, Jim kind of does it all, but certainly when we get down to well data, gravity data, etc., structural reconstructions, he's the one to go to. So, okay, so let's dive into this. Oh, maybe.
The screen before you hear.
Okay. Yep. Thanks, Stuart. Okay. What I want to do first is just give people a look at surface sections. I know most of you have been out mapping, measuring sections and all, but just wanted to get you a little bit in the mood of the tertiary sections. And these, actually, I'll use these in the next slide too, but I'm going to go first and, oh yeah, the mouse does hang up. Talk about the type section. So lithostratigraphy, you probably all know, Bozeman group, lower part is the Renova Formation, upper part is 6 Mile Creek, separated by the Hemingfordian unconformity. Land mammal age, and actually, I won't go into why we prefer to use land mammal ages. Don Lofgren will talk about that in 2 weeks, but yes, that is an unconformity age-wise, probably looking at 21 million years to 16 million years. Renova, for the lithostratigraphic model, primarily fine-grained. You find a type section on the east side, northeast side of the Jefferson Valley. In this particular photo, you do see a channel. So, you know, some coarse grain component to it at the type section. Also ponded deposits, aeolian deposits, which people haven't really talked about much in terms of these tertiary sections, but believe me, there's a lot of aeolian deposition. We're looking at late Duchesnean to middle to late Orellan land mammal ages, basically 37.5 to about 32.4 for age-wise for that. Now, let's go on over to the 6 Mile Creek type section. So, you know, we think we're looking at the upper part, late tertiary part of the tertiary section. And yeah, it fits the lithologic model, looking at coarse-grained units, alluvial fan complex. But the kicker for this is that it's actually a Rickerian in age based on the contained vertebrates. So we're looking at a section, which is the 6 Mile Creek type area, that actually age-wise is below the Hemingfordian unconformity. You know, age-wise, it's approximately 30 to 25 million years. So yeah, I mean, yeah, that's an oops. It kind of messes things up a bit. When Kenzie and Fields then did their paper on the Renova 6 Mile Creek, they opted to retain the 6 Mile Creek as the upper part of the Bozeman group. But if you do a geologic history, boy, you have to beware that not all coarse grain deposits are late tertiary, and specifically 6 Mile Creek type section area is not late tertiary. So, you know, if you're interested in this kind of thing, it would behoove you to take a trip up towards Toston. That plots out about right here, kind of on the southeast edge of the Toston-Townsend Valley. Let me skip around to Pipestone Springs, which is actually world-renowned vertebrate locality has been collected since late 1800s, early 1900s. It's amazing in the amount of vertebrates that this thing has. You can see this is a drone shot. I'm right here running the drone. The section itself is on the west side of the Jefferson Valley. Primarily fine grain. There's a bit of coarser grain material on the southeast end, but turns out this is all aeolian. It had been described in the past as fluvial, no fluvial channels here. It's a good stack up of aeolian in the lower part, which you'll see later in the talk, separated by Paleosols, alpha sols, really common in lust type sequences. Come down to McCarty Mountain, again, looking more in the Eocene area, and that plots up right here on the northern edge of the Beaverhead Valley. And yeah, I haven't talked about footage-wise, but these are all fairly thin sections, although they're pretty typical of surface sections. McCarty Mountain and, of course, the Renova type section are basically the thickest at about 900 feet of Eocene strata. McCarty Mountain, probably there's some faulting towards the south end, so there's some repetition. It's probably more like about 800 feet, but he's quibbling about 100 feet. And then let me just jump over to the Madison Bluffs here, southwest of Bozeman, in the lower Madison Valley. And this is a shot from close to the Madison Buffalo Jump. And what you see here is, I'll talk about these in a bit, Paleosol, calcic Paleosol stacks here, the really resistant ledge-like forming units. But in this particular area, we do have a tuff that we have a 22.4 million year old age on. And actually, if you walk up the section to the top of the jump area, by the time you're at the top, you're in late tertiary. We call it Hemphillian for North American land mammal age, but somewhere around 5 million years in age. So just an idea of sections and footage-wise, yeah, probably Madison Bluffs at 130 feet thinnest, but then we go up to 900 and some feet in section. The reason I'm pointing this out is because at the same time, I started looking at tertiary sections, measuring sections, mapping in the tertiary. There was a big push for drilling in the southwestern Montana tertiary basins. And so started to look at the results of some of that drilling. It was just mind-boggling. In the Deer Lodge area, about 12,000 feet maximum depth of tertiary fill. Big Hole, even more, about 16,000 maximum fill. So, I look at that and I look at these sections and think, whoa, I'm missing most of the tertiary record. So the thought was then how to recover at least part of that, to be able to talk about it and meld that into the surface section. So one of the first passes to make, I think, is always locate those depositional basins. What you're seeing in this particular slide is a Bugay gravity map overlaying a relief image of a part of southwestern Montana. And Jim Halverson, thankfully, contoured this for us. And just to give you some locations, Dillon, right down here, Butte up here, Bozeman over here. So there are several takeaways from this particular image. One is that you can see gravity lows, for the most part, really kind of conform to the present day geomorphic valleys that we know. Deer Lodge Valley, here's the Jefferson Valley. We can see the start, whoops, of the Madison Valley down here. Here's Ennis. Townsend, Toston Valley. Oh, big hole over here. Sorry, Bob, I cut it off. It just got a bit busy, but yes, big hole, significant, as Bob Swartz has already talked about. One thing that you see immediately should be that valleys contain multiple gravity lows. And you might think immediately, those are depositional basins. But let me draw your attention to this particular gravity low off the southeast side of the Tobacco Root Mountains. It would be nice if all gravity lows were depositional basins, but they're not. This one happens to be the Tobacco Root Batholith. So need to be a little careful. And how do you do that? I think the best way is then to go back to these areas where you think those are actually depositional basins and look at the data sets associated with those areas. And kind of notated here, the Deer Lodge basins, for instance, 11,765 feet maximum drilling depth in the tertiary, but the data sets are well data, seismic data, and gravity. Other places we're not so lucky with all the data sets. Madison basins we are. Jefferson, we're stuck with just seismic and gravity. But we go back to those data sets to confirm that, yes, indeed, those are tertiary depositional basins. The other thing to take away from this particular graphic is note the red polygon, 6 Mile Creek, Madison Bluffs. Those are the sections that I just talked about. And note that those sections all plot on basin margins, of course, because we don't have access to deep drilling basins, at least to go out and just measure. So currently, we are looking at basin margin sections when we go out and measure and map. And I'm going to make a point of it later in this talk that that was also the case in Eocene going into Oligocene during the depositional times of these sections that I just looked at. Okay, so we know the location of depositional basins, and we're relatively sure, because of the data sets we have available, that they are in fact depositional basins. We're not looking at a part of the batholith. So how do you get the rest of the data on the tertiary rock record? How do you retrieve that? And what we did, Chuck Wideman and I started to look at seismic reflection data from the different valleys in southwestern Montana where we had access to those data. We were lucky in many cases that we were given access to data in the Jefferson, in the Deer Lodge, etc. But one of the things that we started to notice is that on the seismic reflection lines, there are bright reflectors that continue across the seismic line. Didn't know what these were. Lots of people had different ideas. To get a bright reflector, you need a significant change in velocity, sonic velocity, and density. So there's something different about a set of layers that are giving back a reflection. It turns out we also saw these same features on Nevada seismic lines for the Railroad Valley, and Eric Johnson and Billings had showed us some data, and yeah, none of us had much of an idea about that. But what we decided to do, the Deer Lodge had such a great data suite that we wanted to work there and see if we could figure out what that was. So we talked Jim Halverson into helping us do this. And we picked out one of the wells, MSP 1-25. And first thing we did, of course, was create a synthetic seismogram. We wanted to tie the well data to the seismic line and specifically look at those bright reflectors. So we generated that using density sonic logs. And actually, it turns out we had really nice tie at approximately 930 to 980 meters in depth. So we were seeing a big change in acoustic impedance to generate that. So, okay, we could tie well data to seismic data, and we could follow those reflectors on the seismic data, but what really are they? And so the next step was just to go and try and figure out what is that lithology. And I won't go into detail on it. If you're interested, we have an older paper, a 1994 AAPG bulletin paper. You can get details on it. But basically, we used log suites to determine that what we're really seeing in those reflectors are multiple beds of limestone. So what would generate that in the tertiary? And here's where, I mean, I may have made kind of slight of doing surface measurements on sections and all, but here's where that really comes in to be a critical part of this. We had also looked around in the Deer Lodge, done section measuring, mapping, etc. And what we found is a tie-in and actually a good match to those well logs. These are calcic paleo or pedocomplexes, and you can find those in various areas around southwestern Montana. And what they are petrocalcic paleosols. You know, you're looking at caliche, basically. You find those in the desert southwest currently, but in southwestern Montana, along unconformities, these pedocomplexes delineate those unconformities. You have the one that we actually surface tied to in the central Deer Lodge Valley, and I have that sequence-wise, S3, S4, but it's really the Hemingfordian unconformity. So again, yeah, somewhere around 21 to 16 million years in age. And they're just stacks of soils. And they get up to about 30 feet in thickness. So something that can be picked up on a seismic line. And I just have kind of a schematic here of a calcic soil getting into the mature K horizon over time. How long do these take to form? Work done in the desert Southwest suggest for a very mature calcic paleosol, just one soil, anywhere from 300,000 to 500,000 years for formation. So turns out these calcic paleosols mark other sequence boundaries as well, but that Hemingfordian unconformity, yeah, that's special. There are very well-developed calcic paleosols. So not only do we have one that we surface tied to in the Deer Lodge, but also in the Madison Bluffs, Buffalo Jump, easy to go see those right by the road. Pretty snaky, so I would go in the wintertime. And the Upper Ruby Valley as well. And the thing about these, the reason it also made a great surface tie is that we age constrained these stacks. And for instance, central Deer Lodge Valley, we could constrain it with Barstovian, let me think, Barstovian, let's say 16 to 12 million years in age for a fossil assemblage above the stack. And then below it, could be Midiocene to lower Miocene. But when we started out, all we could do is age constrain these stacks using primarily vertebrate assemblages. Little bit of radioisotopic data that was around, but yeah, not much. So we did really rely initially on vertebrates. And let me just give an idea graphically about the stack up of sequences. In total, we defined 5 sequences. And you can see over here, here's the lithostratigraphy, Renova, 6 mile. 6 mile. I am so used to putting 6 mile above the Hemingfordian unconformity, but in actuality, there's a part of it that's below. So yeah, Renova 6 mile and 6 mile, upper 6 mile, I guess you might call it, related to North American land mammal ages, which Don Lofgren, again, we'll talk to. We'll throw it back to Don. And going back to the sequences, what do they really contain? Sequence 1, bottom bounding, probably the break is about 53 million years in age. The top, about 42. Sequence 1, it's largely volcanics. You can think of Lowland Creek, Chalice, Lower Dillon volcanics. There's also some sedimentary strata in here, the Dell beds and the Sage Creek beds down by Lima Dell area. Those would, of course, actually one of these, the 49.84 is on the base of the Sage Creek, and then the Dell beds would plot up here. So largely volcanic. Sequence 2, that's an interesting one. Yeah, bottom it looks like around 39, and the top up to 31 age-wise. So what does it contain? Well, I'm going to start out and say it contains extensional basin fill. Sequence 2 was the first time of extension. Constenius and others call it orogenic collapse, whatever. It is the first tertiary basins. And turns out on seismic lines, sequence 2 actually thickens into faults, and it's extraordinarily thick. Going back to that Deer Lodge well, I told you that tie-in was basically the Hemingfordian unconformity. So we're looking at about 16 million years to 21 million years there for a break. Everything above that is late tertiary and younger. Everything below it in the tertiary drilling package is lower Miocene and older. But it turns out that that top part, if you looked at it, when I said, gave you the meters in depth to the section, that would mean that the late tertiary quaternary is 3,000 feet thick. Turns out also that well drilled through about 9,700 feet of tertiary. So you have an enormous thickness of basin fill below that, much of what is sequence 2. And we find that consistently in other deep tertiary basins. The bulk of the fill is sequence 2. That's also been found in the Duchesnean as well as the Toston-Townsend basins by Constenius. So it's not unique to what we've looked at, but sequence 4 up here, it's pretty much thin icing on the basins in terms of thickness. So, okay, we have the first basins forming in here, and sequence 3 is it's interesting. It's not ubiquitous around southwestern Montana, at least not that we've found. In others, there are certain places that more of sequence 3, that would be the Araucarian, kind of top of the Oligocene into the bottom of the Miocene. Cabbage patch beds near Drummond, White Sulphur Springs. There's pretty good stacked up sections of Araucarian, but in many places it occurs as Paleo Valley fill. And that is really similar to what one sees in the Wyoming, Dakota Badlands as well in the Araucarian group. And then we jump up into sequence 4, which is, it's the start of the basin range. So another pulse of tectonism, probably some structural modifications on the early tertiary basins. But again, like I said, fill is not that thick. It is, yeah, it's the icing. It's like here is the basin fill. This is basically 2, some of 3, and then there's 4 up here. And of course, at the top, then we get into the Yellowstone sequence 5, that event. And these ages that you see for lower sequence boundaries, upper sequence boundaries, those have come from recently what we've collected for argon, single crystal sanidine ages. Bill McIntosh and Nels Iverson at New Mexico Geochron Lab are the ones who are doing the age analyses for us. I mean, we did have some potassium argon and some glass concentrate data, but Bill McIntosh told me, no, get rid of that. You want to redo whatever you have and go out and recollect. And so we really have tried to collect as close to the sequence boundaries as we can to better age constrain those. And also for the work Don Lofgren is doing, we've also tried to look at vertebrate assemblages and put age constraints on those so we can compare those back to North American land mammal ages, for example, and just see if there are age differences looking at those same faunal assemblages down low and in the US and then where we are in the Northern Rockies. Yeah, Dan.
I just wanted to ask or clarify. So in your view, you would consider sequence 3 for stuff deposited between roughly 26 and 17 MA as 6 Mile Creek?
Okay, so there's the problem with lithostratigraphy. Now I'd say sequence 3.
Okay.
Yeah, I want to be inclusive in terms of the lithologies and also the ages, because you get into a real mess when you go back to what was done by G.D. Robinson in the 6 Mile Creek type section area versus what we all have been using for lithostratigraphy. And also the point that I make is that, you know, we're looking at continental deposits. Think about walking across a valley and you see everything from coarse to fine grain, depending where you are in that valley. Sequences take that problem pretty much away, as long as you can age constrain well. And one thing I want to say about the sequence boundaries, yes, they are unconformities, but we use the definition of Mitchum, which, wow, he put out back in 1977, that sequences are bound by unconformities and their correlative conformities, because somewhere there's deposition that occurs. You know, that's different than the term synthem, which people were using and back in the mid-70s up until the early 90s, where they're just all unconformity bounded units. So Yeah, we go with that. And also the other thing to notice on here, the jagged sequence boundaries, um, the timing, the exact timing of a sequence boundary is not the same everywhere across an area. In general, you can say the timing of that boundary, but keep in mind that, it might be 500,000 years different over by Drummond than it is down by Pipestone. So there's also that as well. And just to give you some ideas of the tuffs we've been sampling, and like I said, yeah, we're really trying to get those that are closest to the sequence boundaries. Here is the lapilli tuff down at Sage Creek. Now that is at the base of that unit. It's not really at the base of sequence 1, but we did that because we really want to look at the contained vertebrates in the Sage Creek beds. So that's one we threw Don's way. And then we're looking at Tufts, Jefferson Valley. Here's one. Sage Creek, also upper sequence 2. Going to the top of sequence 3. Here's a tuff in the Madison Valley. Here's the carbonate, the petrocalcic horizon. Same in the Jefferson Valley. About 1 million years difference in the age, but tuff underneath calcic paleosol stack. And then, of course, we get to the ubiquitous Huckleberry Ridge tuff for the Yellowstone event in sequence 5. And yeah, once again, going back to the vertebrates, I know Don has in mind an extensive talk to walk you through North American land mammal ages, etc. So that will be good. Okay, one last diagram on sequences, and I think this was well done. Constenius and others, 2003. Yeah, Dan.
Sorry,
No, that's good.
Question. That's not clarified.
Yeah.
Where exactly is Sage?
Sage Creek is if you go to Dell and then go east on the Sage Creek Road. I don't know, probably have to go about 6 miles, 8 miles, somewhere in there. It is in that area. So you're if you could go further east on any roads that were open access, you'd end up in the Upper Ruby. Yeah. Yeah, anybody else? Yeah, no, I'm following through this fast. But, okay, this is just a diagram to show you the utility of the sequences and those major bounding unconformities, because those can be tracked from the Great Plains to the Pacific Northwest. And I'll just kind of point out the major ones. Of course, here's the break for us at about 53 million years coming across here. Notice above it, what I call sequence 1. Eric Cheney over in Washington, Central Oregon calls Challis. Don't confuse that with the Challis volcanics. It does contain Challis volcanics, but also sedimentary strata as well. And then if you follow that, note that by the time you get to the Uinta Piceance Basin and the Wasatch Front, it steps up in time. Here it's called the Rocky Mountain erosional surface. And the reason it steps up is because contraction ended at a younger time going south than it did for us. If you look back here, Southwest Montana, Western Montana, Oregon, Washington, we have a volcanic package basically that takes the place of stepping up to still in compression, contraction. And so I would draw ours in at about 42. And so basically the volcanic package is contained within here. Then we can step up, and the unconformity at 42 that we have, we can, yeah, basically take it across to the Rocky Mountain erosional surface, going to the south along the Rocky Mountain front, and we get into the first parts of, for us, basin formation. And so, yeah, we're looking up here, sequence 2, crustal extension. Kurt and others called it orogenic collapse. In the southern Rocky Mountains, the ignimbrite flare-up. Go up to the next one at 30 million. That is an interesting event. That unconformity can be again tracked across a good part of the western US, but what does that mean? What occurred during that time? Kurt Constenius and others, and I agree with this, these are tectonic bundles of sequences. And in the 30 million year event, I don't know, when we first started looking at these, we thought maybe eustatic break, because that matches up with the worldwide eustatic table that had been put together way back when. I don't know, it's really hard to generate a eustatic break all the way up the Mississippi into the interior. Maybe it's the uplift that will then precede basin range extension up here. We certainly see what I would call sequence 3 largely as Paleo Valley fillings in many areas as well as here. And then you step up to the Hemingfordian unconformity. And yeah, that's a whopper. And that then tells us to step into basin and range extension, a lot of input from the Snake River Plain. We can pick it up, well, we pick up the 16 million year events over on the Oregon eastern edge in places like around Bozeman, the Anthony vertebrate locale, etc. In the Madison Bluffs, we pick that up. So anyways, yes, it's really an interesting way to break out units and look regionally, because the utility of these major unconformities it's amazing. You can track those. And of course, we get up to ours for sequence 5. Again, you can track that across. For us, Yellowstone, Washington, High Cascade, volcanics, glacial sediments, etc. So that's all I'm going to say about sequences. Just they've been very good for us to work with in terms of their utility. And the more age constraints we get, the better we have a handle on geologic history. So next, we're going to switch gears. Steve, are you still on? Uh-oh.
Yes.
Hey, all right. Okay.
I just wanted to spare people my face while you were talking. So.
Oh, okay. Let's see. Yeah, okay. I've got you up here, up there. And yeah, I'm not a trace fossil person, but I saw some really interesting things at Pipestone Springs, and I thought they were trace fossils of some kind. So I sent them to Steve, and yeah, we got him interested in coming out, and wow, I've really learned a lot from him. I mean, it's been great. We started out in detail at Pipestone Springs. We have a paper, 2022 paper, that you can go back and read. But the thing about Pipestone Springs, both the north exposure and the south one, man, age control is exquisite here. We have a lower tuff that's 37.5 in age. We have an upper one that comes in at 36. And then we have the main pocket, which really contains most of the vertebrates. And the age on that is middle Chadronian in age. So great age control to start doing these things. And okay, Steve, just tell me when you want me to switch slides.
Sure. Just so I don't go too long, how much time is about left? So I can give you a
Maybe
wrap
about,
up.
yeah, about 10 minutes.
10? Okay, wow, that's
Yeah.
generous. Great. Well, we'll try to fill it up, and if we don't, that's okay.
Okay.
All right. So, what's really important about this area was just when Deb sent me these traces are just about crap because they were beautiful, and there are things that are typical of paleosols and typical of insects and other arthropods, and as you'll see, vertebrates that inhabit these areas in terrestrial settings. So, once I got these and some images, we had gone out there to work with Deb, and it was just astonishing to see these traces. And even more astonishing is they were associated with pedogenic development, with paleosols. And the really neat thing about paleosols and the trace fossils, they could be used as proxies for the interchange between the sedimentation rate or sediment accumulation rate versus pedogenesis. And when that rate slows down, soils and soil horizons are allowed to develop. So in that development, and you can see in this slide where they resemble more resistant areas, and these things represent A and B, multiple B horizons, multiple A horizons, and C horizons of periods of time where the sedimentation had slowed down enough where then the players in this terrestrial ecosystem were allowed to interact, grasses and other vegetation growing, then animals coming in here and eating the vegetation, producing coprolites and other types of dung that allowed then beetles and other insects in here to make use of the dung and bury it into the soils. And you can actually see successions of these within those soil profiles. So that's actually pretty damn incredible, and the preservation is fantastic because of the sediment that's involved here. So in this particular picture, you see at the very top, there's which would be an example of a vertisol, and we'll see that in the next slide. And then those other arrows are pointing to a variety of alpha sols. Some are continuous, you can see across the slide. Others are in between the one alpha sol and the vertisol. And then even lower, then we have a number of inceptosols. So those tell us that those are periods where the sedimentation rate slowed down enough. So alpha sols are a bit more mature and they're a bit more better developed. Vertisols can develop relatively quickly, but they're self-mulching and very diagnostic. But each one of these is basically preserving the individual organisms that interacted on the landscape. Well, if you guys have any questions anytime, just tell Deb and I'll take questions. So yeah, Deb, you want to go to the next slide?
Got it.
Great. So here's an example of a vertisol, and it's fantastic because you have what would be micro highs and micro lows back up to a micro high, and all that knobbly character within it are actually trace fossils. Every square inch of it is some sort of animal burrow, and these are predominantly made by Coleoptera beetles, and mostly by dung beetles, and then by some moths, and then some other relatives of the beetle making meniscae backfill burrows. And then we've also found a variety of sizes of wasp cocoons and bee cells. All right, Deb, you want to go to the next slide?
Got it.
Yeah, so here's a close-up, and one of the images that first Deb had sent was in that upper left side. And you could see these little cup-like things where they're more resistant and material has weathered out of it. Each of those is a trace that cross-cuts another trace that cross-cuts another trace. So each of these, depending on their morphologic features, can be given a different name. So that upper right-hand picture, those cup-like things are typically referred to as phaeoichthys, and those are typically a remnant of a dung beetle nest. And then below, there in the middle, eaton-ichthys, which were originally thought may have been made by wasps. Those are also some sort of either beetle or large moth larva burrow, things that lived in the soils at the time, and they make these pelleted structures, and then the inside is would have been hollowed out where the larva was and then later filled. And then there below it in that column is what's referred to as a dung sausage. If you look at modern types of dung beetles you see operating in the Netherlands and in the Serengeti, they make these structures where they hollow out an area and they backfill it with sediment and dung. And then they would lay the egg on the top there where the cup is, where the red dot, and then eat it out through. And then right next to that, a trace called rebufficnus, and that's typically made, that could be either produced by a beetle larva or a moth larva, and there's a number of those in the sections. And then even more incredible to the very end, there is something we just called a rosette pattern or rosette burrow, and it shows these patterns of meniscate backfill all the way around, but it's basically the construction of this subterranean nest by the adults. Then that would then the female would lay the eggs, and they'd either bury the whole thing and move on, or it would be left open and they would basically guard the nest. So what we have here, in essence, is the reflection of all this dung beetle activity. So what does that mean? It means that there had to have been vegetation nearby and grasses for vertebrates to feed, and a number of those vertebrates are represented by the fossils that have been collected there by Don and cohorts. Right, so it shows that their presence is there. They're leaving dung. Dung is being used by a number of these beetles. It's being buried in the subsurface, and then these larvae hatch and start the whole cycle over again. So the same thing when we see these wasp cocoons in bee cells, which we don't have pictured here. The wasps are feeding on other insect larvae that are there, but there's adults that are feeding on. They kill the insects and they bury them in the ground. Bees are there, the pollinators, and they have their nests in the ground, so they're soil bees. So you get this whole ecosystem represented here by the trace fossils, and then of course the bits and bobs of the vertebrate material that's been collected here. So go ahead to the next slide. All right, so we see similar things over in McCarty Mountain, but it basically upped the ante. There's these things that from which Mr. Douglas there had collected all sorts of vertebrate fossils out of. He called them nodules or concretions. But when Deb had taken me out there, these are actually vertebrate burrows. And vertebrate burrows, you don't hear much about their preservation. People thought that they're really hard to preserve in the rock record. But as you can see from all the measurements and work that Deb has been doing for us for a presentation we'll be giving at a GSA coming up, these burrows are very large to smaller. They represent a variety of complex networks of subterranean features, and a number of these are the things that have yielded vertebrate remains from. But these are also preserved with the dung beetle nests of like Phaeoichthys and the dung sausages. To the left is a trace that looks like eaton-ichthys. So you can actually see the top and the sort of spiral pattern of pellets. So very, very, very compelling for the representation of this ecosystem that's been frozen in time, and explains, why you get vertebrate fossils and nodules. And if you go to the next slide, and I think this is the last one for the Paleosols, that these things are huge. So it represents a number of different burrowing vertebrate animals here of various sizes. And some of these burrow networks have smaller burrows associated with them. So maybe the juveniles who were burrowing and learning to burrow, and depending on their relationships, had the larger adults. And from the size of these other complexes that we could follow over tens of meters, these are probably representing family or extended family units of the vertebrates living together here. So it would have been the mini horses, and Don, you could chime in. I don't know my vertebrates very well, unfortunately, so I apologize. But, you know, this is showing a lot of what was going on at the time in this ecosystem that was supported by a great variety of vegetation. So with that, I think I'll wrap up the burrow part in the paleosol part. So even these things here are parts of a paleosol. All right, so they're not just a burrow with a bunch of bees and wasps and beetles. They are components of soils.
Yeah, thanks, Steve. Yeah, and that's pretty much it. Now, I have to show you this summary slide. Chuck put it together. Previews of the same data. So we've had 3 talks. There are some maybe major differences in some of them, but you know, we kind of all work together and get things melded. So yes, I guess we can take some questions. Thanks, Steve. Yeah, Stuart.
So, you know, we're trying to map these basins. How would you go about mapping these? Do you use the names Renover, 6-mileage, Bozeman group? How do you go about it?
No, I would just use sequences. You saw on that regional extension of unconformities, Eric Cheney, who we have worked with, Eric decided that he would name his sequences. So that's why it's Chalas, Kiritas. He used indigenous groups. Kurt Constanius tried to talk me into doing that, and that probably would have been a wise thing to do rather than 1, 2, 3, 4, 5. But yeah, I would map them as sequences because then you know the age. You have the age control. You don't have the problem of what we saw in the 6 Mile Creek type section area that really it's a rickeриan. And so that's what we do. So that would be my suggestion. Anybody else? I guess we're all going down to, oh.
Do we have one in Zoom land that wants to ask a question?
Oh, yeah. I didn't even think about that. Let's see. Let me see if I can pull everybody up. Okay. So anybody out in Zoom land that wants to ask a question? Otherwise, we're off. Oh, Jesse.
Yeah, I like the sequence approach. Anyway, have you looked at the tertiary section, like south of Badger Pass, like the east slope of the Armstead Hills, and you go around in there at all?
At Mill Point in the rickeриan.
On the other side of Badger Pass, on the Beaverhead side.
Not much.
So this nice sequence that I mapped there where it's, you know, like channelized sort of conglomerates and sandstones, barely liquefied. I did on the sandstones, I did some zircon dating.
Okay.
Max depositional ages, you know, somewhere between 25 and 21 in May. So kind of those are max depositional ages.
Yeah.
For taking consult, but
Right.
Anyway, it kind of it's, you know, seems like it might fit in there with your sequence 3, and you know, it seemed like if we were to take use those max depositional ages, you know, it seems kind of young to call it Renova, maybe not. I don't know, depending on who you ask, but then you know,
Right.
below the unconformity, the 16 MA,
Yeah.
everyone wants to call it maybe on that 6 mile So it kind of seems to fit in there with your sequence three. So like in a case like that, when I'm trying to compile this 100K map, you know, what should I call it? You know, just give it a name or call it, you know, like that's kind of what I've been doing is like naming things locally, especially where I don't have good age control and I don't like straight logic approach and garbage cleaning, all these things. So,
right.
yeah.
Yeah, you don't know what you're really ending up with. I mean, some older gravels, you can look at the weathering rinds and kind of know you're back in Eocene, early Oligocene, but
So many places.
yeah.
And the bill 100K where we just don't have age control.
Right, I know. Yeah, that makes it tough.
But in that particular case, like what would your advice be to me?
Man, I would
You
still.
call it 6 mile because you had it 6 mile in your correlation chart.
Right. No, I would never use lithostratigraphy. I guess I really differ with Rob on that. I would go with sequences and whatever, even if you think you take that with a grain of salt for your zircons, still that's better than just, you know, throwing it in a garbage can and
Right.
yeah, just saying because it's coarse grained, it must be this. Because that just, that leads to lots of problems. And I like your idea. We talked about that, you know, doing things locally because, if you think about these depositional basins having formed early on, you're going to see influx of different lithologies into them locally. So, I think that's a great approach. I like that. Yeah, and when we talk to you about the beaver head, whatever the beaver head is.
Yeah, that just has it.
That's why, I mean, I have it on my charts, but I didn't touch it because, that's a whole nother thing. But the way you look at it, and you do that locally as well. And so, at this time, I think that's the best thing to do. Yeah, Stuart.
How would you feel if personally, if like we ditched the formation names, but retained the Bozeman as a group and put the sequences within the group?
Well, then you're mixing lithostratigraphy with sequence stratigraphy. So, I mean, if you want to go with sequences, do what Eric Cheney did, just, decide. Because you never want to mix those two. It's just confusing. Anybody else? I mean, as you can see, there's a lot of really interesting stuff out there in the tertiary. And got a long ways to go, but it's good you all are working in it. That makes database better and it really progresses.
I was also going to ask, what basins do you have evidence of faulting in sequence 2? Like, I'm wondering if there's any evidence of that in like the Beaverhead Valley.
Beaverhead is really pretty shallow. Yeah. So, you might be looking strictly at sequence 4 basins. I'm talking about where we're looking at 16,000 feet fill, 12,000. So seismic data we've looked at would be Deer Lodge, Jefferson. Chuck even had a student that reprocessed Jefferson, both depositional basins. Kurt Constenius did detailed work on the Duchesnean, and also it's proprietary, but he did show us work that he did on the Townsend Toston as well. And you could see those features. In fact, if you go back to that 2003, I think it's an FCPM paper of Kurt's, he talks about that in there as well, and actually lists the basins where he has seen that thickening in the subsurface. So that's the other thing about combining surface with subsurface. A lot more data, and you can see features that you just wouldn't pick up on the surface because you're just left with those basin margin sections. Yeah, Jesse.
So, but sequence 1, that it seemed like you had some ages around 49, around Sage Creek.
Right.
Yeah, so I've been getting a lot of similar ages out of that Dillon Vulcan, the pile, the
Oh,
volcanic rock south of Dillon, one.
right.
That whole area. So do you really think there was absolutely no extension happening at that time?
In the sequence one,
Yeah.
I think that was the precursor, probably some extension, but haven't been able to pick it up. Can't see it on the seismic lines, hard to image through that. So, yeah, I would think so, but just, it's tough to document it.
Yeah.
Yeah,
One last one.
okay.
So with the having 40 and unconformity, I'm wondering, are there any places where there's continuous deposition through that you know of? And then what sort of range of ages on the, like how much variability is there on the age range that's represented in that unconformity?
So I showed you in the tuffs we collected 1,000,000-year range on there. And it's probably greater. Actually, what you could do is, I mean, this is just ballpark, but you could look at those Paleosol stacks. And if you think about, anywhere from 300,000 to 500,000, you could get a pretty good age breakdown there. I mean, it would be better to actually document that with ages, but you can do a ballpark figuring on that. And for sedimentation, I think the Williams Creek area, as you go into the Ruby, might be the closest. I mean, the Heming-Fortean unconformity is, wow, that is so distinct. And I mean, honestly, the Paleosol stacks are the best developed on that unconformity. So it's pretty tough to find deposition there. But, probably you could look outside of southwestern Montana and find that. But offhand, yeah, I can't think of any. It's just, yeah, it's a boomer. Yeah, anybody else? Well, once again, thanks. I mean, I think this is really a great forum. So I appreciate you all doing that and being here and in Zoom land as well.